Morning, ladies and gentlemen. The usual, really non-announcements. However, Project 2 deadline next Tuesday. Homework. Oh, this one. Labs tomorrow and Thursday. There is a small lab that you're going to do on the stuff that we're currently working on. And then there will be project time. So there is actually a lab. Unlike, I think, last time when you had Project 1. It was all lab time? Yeah, so at this point, you are much more familiar with the coding, and frankly, I think maybe in Project 2, the coding is a little less demanding than it was in Project 1. Or everybody's getting used to it, and I think it's a combination of the two. So we're going to give you a little lab in addition to Project, so please go to lab. In response to numerous inquiries, I've got the course that we are calling Prob 140, which is Statistics 140, is now online on Cal Central. You'll find it there. Before I spend a lot of class time talking about it, are there people in this room who are interested? If the people watching the video are interested, they can get in touch with me by email. But here, before I waste your one, okay, there's a few. All right, so the typical question that is coming to me is if I take 140 and I want to get into the stat major, what happens with stat 134? If you don't know what I'm talking about, tune out and do Facebook for a while. This is a pilot course, and there have been no official decisions made. However, I have little doubt that this course is going to cover essentially the chunk of 134 plus Python, so it's going to be the math as well as the Python, because you are coming in with a prereq, which Stat 134 doesn't have. So for this semester, students who get the requisite grade level in 140 that they had to get in 134 to get into the major will be able to petition to not have to take have 140 stand in place of 134. That is for the statistics major. I cannot vouch for any other department. So if you are thinking of you need 134 for the math major or for the econ major, you should probably take 134. But for stat and for data science, and of course, there isn't a data science major, but we're hopeful that at least shortly there will be a minor at least. I am very confident that 140 will do whatever it was that 134 would have done. So if you are in Data 8, and especially if you are in Data 8 and Stat 88, or if you are curious about the mathematics, 140 is an interesting option to try because you have skills and a background from Data 8 that the typical Stat 134 student doesn't have when they're coming in. And to capitalize on that background is a terrific thing to do at this stage. That is exactly why I developed 140, because now we have 1,000 students on campus who really know something about randomness. So for them to come in and use, not just set aside all the Python and work with pencil again, but to use the Python to confirm what they are now discovering by mathematics, I think it's going to be a lot of fun. We're having a blast developing it. It's going to be a great deal. It's going to be a lot of fun. So that's my little spiel. I will take questions. Yes?
Besides Stat 88 and C8, what are the other math prerequisites?
Stat 88 is not a prereq for Stat 140. The prereqs and we're calling it Prob 140 because now Data 8 started a trend. Every course now has a nickname. So your course is Stat CS Info C8, affectionately known as Data 8. So I have students writing to me saying, is Data 8 not being offered next spring because I can't find it on the online courses. They are searching for Data 8. Poor things. So Data 8, there's Data 8, and now there's DS 100, which is tentatively going to be offered, almost certainly going to be offered next spring. There's nothing called DS on campus. That course is actually CS/Stat 100, but it's affectionately known as DS 100, and so this one, which is Stat 140, is known as Prob 140. That is not at all what I was being asked. But hence the name of this course. So Prob 140, prereqs, Data 8, a year of calculus. That's it. Now, if by a year of calculus, students have very different backgrounds, we don't actually do very complicated integrals. So people who come from BC calculus can do all kinds of integrations involving trigonometric functions and powers and so on and this and that, and it's all wonderful. But what you need to understand is what's a function, what's its inverse, what's the composition of a function, what's a logarithm, what's an exponential, etc., etc. That's what you need to understand. So in some sense, even having done a lot of computational calculus is not the issue. It's understanding the abstraction of what functions mean, especially exp, log, and so on. That's going to matter. Any more questions? Yes? Will it be offered in the fall? Almost certainly not. The following spring, I hope so. All right. Enough about that. So DS100, I still don't know about its approval. The minute I know, I'll post on Piazza. Actually, somebody asked, and I think your question just answered this, somebody asked, do I need to take Stat 28, that's the other new data science course, before I take either Stat 140 or DS100? No. Stat 28 will teach you methods of data analysis, more involved data analysis than what we're doing here. But it is not going to do the math. It has no math prereq. It has data 8 as a prereq. And it's not going to demand, sort of programming ability like DS100 has CS61A as a prereq. So they're sort of off. All three of them are not on the same axis. And so you can take any combination, really. Okay, to work. Last time, summary. We had a measure of linear association. That means how tightly clustered points in a scatter plot are about a straight line. And there is the measure, the correlation coefficient R. I gave you a mysterious calculation. At least today, I hope to be able to show you where that calculation came from, if not why it's exactly that formula. But at the end of that, we had a number that was between -1 and +1. You know what the extremes mean. You know that R equals 0 means that there's no linear association, but there could be significant nonlinear association. And you know that R is not affected by the units of measurement, nor by which you call X and which you call Y. And we also talked about being a little sensible in using this number or interpreting this number for particular sets of data. That is basically the 2-minute summary of last time's lecture. The main use of correlation is in prediction. So you have the value of one variable and you're trying to predict another. That's somehow where we started last time. And we have done predictions in this class. We have predicted, we have used Galton's data and predicted child's height based on mid-parent height. And at that stage, we had no idea what R was. We made the prediction anyway. So that is the first thing for you to keep in mind, is that you know how to make predictions regardless of whether you have correlation or not, whether the scatter diagram is linear or not. You just know how to make predictions using, take your given X, take all the points that are near it, predict by the average of those Y's. Right? However, these things are done over and over again, so it's a good idea to see if we can automate that process a little bit more. And especially when you're seeing something as clear as a straight line in a diagram, it is nice to be able to identify that line. And in identifying that line, we will be able to see some properties of these predictions that aren't necessarily obvious if you just compute them in the way that we've done here. So today, the business is going to be, if the scatter diagram looks like that, that shape is called a football shape, which is extremely confusing to people like me who come from some other background where footballs are round. This is the American football shape, oval shape, formerly known as bivariate normal. We won't be using that term. But you can see this is a football-shaped scatter diagram, and the axis of a football is a straight line. So we are going to today look just at football-shaped diagrams. And do you recall that SDs are actually hard to spot on curves unless the curve is normal? Yep. If the curve is normal, you can see roughly how big NSD is. So also, when the scatter diagram is football-shaped, you can see what the line has to be that you should be using to make your predictions. There is a miracle of mathematics that makes that line that you have identified on a football-shaped diagram also the best thing to use for any other shaped diagram. That will be the business of Friday. We won't do the mathematics, we'll do it computationally. But for today, we are just going to focus on the football shape and just figure out what this line needs to be. We are going to use Galton's data for a reason which is, I guess, I want you to understand where this stuff comes from. Who came up with this? And Galton and Carl Pearson came up with this stuff using these data, and retracing their steps is valuable because it helps us understand the properties at every step. Then on Friday, we will return to the modern world and use our computational power to deal with data sets that don't look quite as beautiful as this. But it's important to, today we're just going to pretend we are Galton, and we're trying to discover what that line is. So that's the goal. So here we go. I'll just remind you of, this is all stuff from before the prediction that was on the slide. I just want to run it so that it's all live. Okay. So that's the same picture that we had before. I would just like you to note that I am now saying this is our original prediction because pretty soon we're going to have a different one. Okay? That's the only thing that's changed. That label has changed. Okay. So now what I want to do is I want to look at this oval and the line going through it, and I think you will agree that when you see is it oval or not, you're just looking at the cloud of points. You are not looking at the numbers on the two axes. Yes? Is there a line going through it? You are just looking at the cloud of points. You are not looking at the two axes. The minute you have something that you can spot without looking at the two axes, in your head, you're in particular units. What units are you in? You are in standard units. Yes? So we're going to play this game again in standard units now, so that we are not dealing with inches on the two axes, but just how many SDs away from average. So I recall our function, standard units, and I am going to apply that, well, it's not really apply, I'm just going to use that function on the array, the two arrays. Let me show you. That's what heights look like. We are just going to convert this array to standard units and this other array to standard units. That's what's happening here. And in standard units, that table looks like this. And so what we're going to do is we're going to take, given a mid-parent height in standard units, we are going to predict a child's height in standard units. Okay? So what did we do here? Given, supposing somebody gave me 72.06 at the mid-parent height, what would our program have done? So the given height is 72, the parent's height, 72.06. What would the program do? It would try to identify which points? Okay? Right here. I want you to do it without the program in front of you, because you need to remember what the goal was. So basically, you're given a mid-parent height here. Now what does the program do? Which points does it work with? The ones close to that, right? So all the mid-parent heights that we define close to be a half an inch away. So it goes half an inch on either side, so that's 72, 2 inches, so it goes about this much on either side. It takes a strip up here, and it calculates the average there. Yep? So now, if we are given a mid-parent height of 1.58 in standard units, then we are going to find the points that are close in standard units. Yep? And we're going to find the average height of the child in standard units. It's the exact same game, just going to be played in standard units. The one thing we have to do is we have to define now what close means. previously we had said close was 0.5 inches. And the reason I'm going through this exercise is I want you to be able to move between the inches scale and the standard unit scale. Measuring heights in inches, you understand. You've been doing that for a long time. Now, in standard units, you measure in SDs, right? You call the center is the average is 0, and then you're walking in units of SDs. So what you need to know is what is an SD of mid-parent heights? Okay, so that's about 1.8 inches. Right. Now, 1.8 is a nasty number. Supposing that was 2 inches, right? Just be a little rough here. Supposing that was 2 inches. Then our 0.5 inch, the plus or minus that we were using, the 0.5 inch would have been how many SDs? If one SD was 2 inches, then half an inch would be how many SDs? A quarter of an SD. You agree? And the calculation there is you would take that 0.5 and you would say 0.5 relative to an SD. So 0.5 divided by 2. Yep, and you would get a quarter. So we're going to play the same game here. We are going to take 0.5 and we are going to divide by this nasty number here. And so our distance of 0.5 inches corresponds to 0.28 roughly standard deviations. And that is the appropriate distance to use in our new game when we are playing in standard units. We got 0.5 because that was our original choice that we made weeks ago when we defined what close means, this 0.5. Right? And last time we saw a little bit of the effect of changing this number. But I'm sticking with this was section 7.1, functions and arrays. We had done this prediction, and we had chosen 0.5 then. And I'm being terribly conservative, and I'm just sticking to that. Okay, so before we run our new function in standard units, are there questions about measuring in SDs? Yes? What I'm doing is, so 0.5 is an amount in inches. This is 0.5 inches. The SD is an amount in inches, 1.8 inches. What I'm saying is 0.5 inches is how many SDs? All right, so it's 0.5 inches relative to an SD, so it's basically a pure number that I'm getting at the end. What we have realized is that half an inch is approximately 0.28 of an SD. So you can think of 0.28 as a fraction. Is that many SDs? More questions? Yes? Can I re-explain the standard units function? I will show it to you. It's how many SDs above average. So you calculate the distance above average in inches, and then compare to an SD. Divide by SD. Yes?
Is that 2.8 in standard units?
The 2.8 is the number of standard deviations, yes. More. It's good to have the questions at this stage because this is the first time really you're moving back and forth between units and wholes at this stage. Yes? What's the difference between deviations and units? Explain to me your question again. So standard units mean how many SDs above average. And what we're measuring is how many SDs. All right, we're just measuring distance, not where it is on the horizontal line. So we're just measuring how far do we have to walk, not where will we end up. Standard units measure where you will end up, away from center. All we're doing is how far do we have to walk from our point. Does that help? All right. So we are going to do our prediction in standard unit, and I have, you know what? I'm going to totally erase this thing. We are going to take our original function and put it in here, and you are going to tell me what we are going to change. Okay? So def, do I change that? No. How about this? Well, you know what? I'm going to change it because I want to know that this is working in standard units. So is that okay? Yep. All right. So the reason, when you define functions, the names that you use, they are for you to be able to go back to your code and understand what on earth you were doing. Right? So here, where we have mid-parent height, I am now going to give it a mid-parent height in standard units. That is why I am changing the name. If I had just left that name as is, or if I had simply replaced it by Fred, the program would have worked just fine. But when I came back, I would not know what I would have done. So that is why I'm changing the name. That's the only reason. Okay, so the comment, return a prediction of the height of a child, well, not quite, the height in standard units. Agreed? Whose parents have a mid-parent height in standard units of this new thing that I called mid-parent height SU. So far, so good? The prediction is the average height, okay, here we go, in standard units of the children whose mid-parent height in standard units, this is so boring, is in the range this thing, plus or minus 0.5 inches relative to the SD of mid-parent heights. And that is, none of that is a program. That is just me telling myself what this thing is taking and what this thing is trying to produce. So before we move to the program, could you please read that red comment and tell me if you have any questions?
Why don't we say is in the range and mid-parent height SU plus or minus 0.277?
We could say plus or minus 0.277 SDs. We could have done that. That would have been just fine. It's just going back, I would have lost in my head where the 0.5 was. Right? So when I look at the two functions, the first one has a 0.5. I just want to bring the second 0.5 back. And that is why I'm not using the number. In fact, I'm just going to define close to be 0.5 divided by the SD, what did I call it, mid-parent. I'm not even going to put the number 0.277 there because I won't know where it came from. I could. It would be correct. Okay, close points. Heights, not heights. It's heights in standard units. That was the name of my table, was it? Yes, heights in standard units. Okay, heights in standard units where mid-parent, I believe, in standard units, mid-parent in standard units are between, okay, so this thing is now in standard units and we're subtracting off the number close and we are taking the same number and we are adding the number close. Can somebody tell me before I go to return, is that a correct transformation to make? You see anything I'm missing? So this is the heights table in standard units where the mid-parent height in standard units are between our given thing plus or minus this number that we have defined to be the degree of closeness. Move, go back, or I have another line to work on. Yes, but before I move to the return line, this long line that we just wrote, are we good with that? All right, so what we're going to do is now we have close points dot column. Child is no longer in original units, it's the child in standard units, and now I have a program. So this is what I do every single time when I'm writing a function, especially if it's a function that's like something I've written before. You start with the first word and see what do I have to change. So I'm actually terrified when I look at your code. People come to me with code, their homework, and it's one line. The entire calculation, 3 columns of a table. It's table with column, and the thing just and I'm zigzagging and feeling seasick. I implore you to write in little bits, please. Because it's much easier to test in little bits. Okay, so we're going to define this function, and then we're going to run the function. So this is our original heights standard units table, and we're going to apply this new function that we have defined, and this is going to take a while to chug. So this is my backhanded way of going a little bit slowly through the coding, because once you look at the picture that arrived, that should look like a very familiar picture. It is the exact same picture as before. It's just the axes are now -4 to 4 standard units. Yep. So all of this is a confirmation that you can play this whole game in standard units, and that's going to be really important for what follows. So just to confirm, that was our picture in standard units, and that was our picture in original units, and the only thing that's changed is these numbers and these labels. The picture itself is exactly the same. So now what we're going to do is we're going to say, okay, we can work these predictions in standard units only. So we will draw pictures only in standard units, and so what I'm going to do for you is I'm going to draw you an oval. In standard units. And remember that we're trying to identify the line to use for our predictions. So when you have an oval in standard units, then both both variables are on the same scale. The x equals y line is a very natural one to draw. The 45-degree line is a very natural one to draw. But it's not a good line for us. It's there because it's natural for comparison, and it is, an axis of the ellipse. However, what are we trying to do? If I give you a mid-parent height here, you have to predict the child's height, yeah? So what are you going to do? You're going to go up this strip right here, and you're going to find its center. Agreed? Is that its center? I don't think so. So here's, if I'm given a mid-parent height of 1.5, then the children's heights go from about there to about there. That's too high to be the center. Yep. That 45-degree line is the wrong line. It is the easy line to draw, but it is not the line to use. The center is a little bit lower. The center somewhere here. So the line to use is flatter than the 45-degree line. And let me draw, let me draw the line for you, and then I'll take questions. So the red line is the easy line to draw, but it's the bad line. That's why it's in red. The green line picks off the centers of the vertical strips. So if I look at the vertical strip here at 1.5, then the children's heights are from about here to about there. That's about roughly in the middle. If you take -1, then the kids' heights are from about there to about there. That is the middle. This one's too low. So the line that you want to use for prediction, what you are noticing is that it's flatter than the 45-degree line. And before I get into slopes and things, I'll take any questions about the discussion up to this point. Yes? What's the point of using standard units when it creates the exact same picture? So the question is, what's the point of using standard units if it creates the exact same picture as before? Because when we work in standard units, we cover every single scatter diagram. Right? It doesn't matter whether it's inches, pounds, kilometers, acceleration, anything. Every single oval scatter diagram I'll deal with at one go. So we'll work in standard units, we'll figure out the line in standard units, and then we will convert back to the original units. Okay, the point in standard units is to be completely general. Okay, so the green line is our friend. The green line is the one that we are going to use for estimation. And now we're going to talk about the slope of the green line. One thing for you to notice, please, it should come as no surprise that both of them go through the origin. Right? That's the average of x and the average of y. If you're given the average of x, you will predict the average of y, no matter what line you're using. Right? If the line is sensible at all. Okay, so the green line is a line that is flatter than the red line. All right, so let's go back to middle high school. What is the slope of the red line? It's the 45-degree, and slope is 1. So the slope of the green line is, so I'll ask you a few questions. 0, positive, or negative? The green line. Positive. It's sloping up. Yes? So the slope of the green line is bigger than 0. Next question. Equal to 1, less than 1, greater than 1. Less than 1. It is flatter. The slope of the green line is a number that is between 0 and 1. It's a positive number and it's less than 1. A positive number less than 1. Oh dear, what could it be? What do you think it is? R, there you go. That's Galton's observation. And it is through identifying this line and this slope that the formula for R came about. So that mysterious thing that I gave you last time, convert to standard units, multiply and take the average, it's from this calculation that appeared. And Galton couldn't do it. He wasn't a mathematician. He went to Pearson. And so this correlation is called Pearson's correlation, and Python actually has a function called Pearson R. It's the same thing that we described. Okay, you've got the line. You're done, apart from changing units. So I just want to convince you that this is, in fact, a good line to draw. So I have a little routine here called regression line that will draw lines. I'm going to start out with the extreme case. What it takes is R as its argument. It draws the scatter diagram, it draws the red line and the green line, right? So I'm going to run it. The absolute extreme case is R equals 1. If R equals 1, 3 things are the same. The scatter diagram, the red line, and the green line. They're all exactly the same. Okay? Of course, R is never 1. R is less than 1. So what we're going to do is we're going to change this. We're going to drop R a little bit, 0.95. And now you see the green line begins to separate from the red line. Yep, the minute you introduce spread, the line of predictions starts to drop. It gets pulled away from the red line. And if you do 0.6, clearly different. And by the time you're getting to 0.2, it's getting to be flat because there's no information here. Yeah? So what you can see is, because you're working in standard units, you can see how the regression line behaves. This is called the regression line for reasons I'll explain in just a moment, how it behaves for various values of R. Any other value of R you want me to try? 0 was the request. That's a good request. Flat. No information whatsoever. Is R always positive? No. Same thing. Just nobody likes drawing downsloping scatter diagrams, so we always work with upsloping scatter diagrams, and many of the relations that we want to study are upsloping anyway. Okay. All right. So what I'd like to do is give you an upsloping one. Okay. So Galton was doing this. Galton was doing this why? Galton was a eugenicist, and he wanted to breed Superman, and Superman has to be tall. They just have to be tall. Forget the brains. They have to be tall. So, great. So, he wanted tall parents to have tall children. And now I want you to look at this line. Look at the parents who are exceptionally tall, 2 standard deviations above average. Yeah? Where is your prediction for their child's height? Right here. Yes? Is that 2 standard deviations above average? No, because if it were, it would be on the red line. It is less than 2 standard deviations above average. And so what this vertical spread is showing you is that given a value of x, your prediction for y is less extreme. It's closer towards the mean. So for the exceptionally tall parents, you do predict that their children are going to be tall, but not quite as exceptionally tall as the parents. And this pissed Galton off, because this is messing up what he's trying to do. And he wrote a paper, the title of which includes the wonderful phrase, Regression Towards Mediocrity. And that is why we have the name. And it is a good name because it picks up exactly what is going on. Exceptional on one variable, your prediction will be somewhat less exceptional on the other. Now, on the other side, Galton was a scientist. He looked at the exceptionally short parents. And he realized that their children would be comparatively a little bit taller on average. He didn't care. He didn't care about those people. He was just interested in the tall people, so he just stayed upset. But you should be looking at two variables, every pair of variables in your life, and keeping in mind the regression effect, right? The Warriors win their championship 1 year. The next year, regression effect. When you are at the tippy top of a distribution, the only place you have to come is down. Right? There isn't, on average, you expect they're going to come down. So all those of you who did brilliantly on the midterm, I loved it. It was a pleasure looking at your exercises. I'm just saying that, this is kind of working against you. So what you have to take in is that regression is a statement about averages. Those who are very high in one variable, on average, we expect them to be a tad lower on the other. But that doesn't mean everybody's going to be lower. So you got to be the person who beats the regression effect, right, and be very high both times. On the other side, those who didn't have such a great day on the midterm, that is working for you. If you just continue on your merry way doing exactly what you did, I will predict you'll do a little bit better. Now, you also can beat this prediction and do quite a bit better. This is a prediction on average. I have umpteen stories of what is called the regression fallacy, people noticing this and just going crazy ascribing causes. But I don't have to, we'll go through our equation today, and then we will come back and waste time telling stories. Okay, so I will pause for a second and summarize. Football-shaped scatter diagram. The regression line, that's the line on which your predictions lie, is a line that passes through the origin and has a slope that's less than 1, and that slope, by definition, is the correlation. So if we know that, we have a line that passes through the origin and has a known slope. Can we not write down its equation? We know how to write down equations of lines. So any line that passes through the origin has an equation of the form y equals what? Slope times x. There is no intercept. Agreed? Okay, so can you read that? Kinda. Yeah, okay. The equation of the regression line. Okay. What is on this green line? It's your estimates or your predictions. So the estimate of y is the correlation times x when both variables are measured in standard units. That is what we have just seen. And I would like you to take a look at that and ask me any questions about that equation. That is the equation of the regression line. If it has looked different in some other class, or if you feel that just looks too easy, it is that easy. The complication arises, it looks more fancy when you introduce the original units. But regression is that simple. Measure your given thing in standard units, multiply by r. That is your prediction. It's in standard units. And so just to check that we know how to use this line, I'm going to go back and do... Okay, so that's the equation that we just wrote. Example of use. If r is 0.6 and I tell you somebody was 2 SDs above average in x, then your prediction is 1.2 SDs above average in y. Why 1.2? Because that's 0.6 times 2. That's it. That's your regression prediction. And we just said that on average, the regression prediction says that y will be a little bit closer to the mean in standard deviations than x was. So let me have you do a little estimate on. So we've got a class with a midterm and final, and the two scales are different. This is John De Niro's example, and you've got a football-shaped scatter diagram and a correlation of 0.5. Then, okay, this is a garble here. This means, what do you expect the average final score would be for students who scored 90 on the midterm? John's slide was not garbled, mine is. Okay, so you've got all the data you need, and you've just seen that your prediction is in standard units is r times whatever you're given in standard units. Okay, now find somebody to work with, work out what you're predicting. First, figure out what you're given in standard units, then use regression. Right, 90 points on the midterm is how many standard units? Sorry? 2. Why is that? It's that many SDs above average. How many points above average? 20 points. 20 points is how many SDs? 2 SDs. All right, so your calculation is 90 minus the average, that's your 20, and then relative to an SD. Okay, so you're given 2 standard units for x. What's your prediction for y? What do you do? Multiply by r. That is what you just learned, right? Take your 2, multiply by 0.75. Your prediction for y is 1.5. And you're kind of done if I had asked you for standard units. Right? So your prediction is 1.5 standard units. But I want points. Right? So I want to know how many final exam points that is. So 1.5 standard units means what in English? 1.5 SDs above average. So I need to go to SDs of final exam scores. That's 12. 1.5 of those is 18. You agree? And then above this average of 50, I get 68. Questions about this calculation? It is a direct application of our equation of the regression line written in standard units. Your prediction in standard units is r times the given value in standard units. And the rest of the class is going to be devoted to just writing the same thing in the original units. How did I get 2 standard units? 90 is how many SDs above average? That's the question. Yes? So it's 20 points above average for the midterm. The midterm average is 70. Yeah, 2 variables. Got to pick the right average. Okay. Next. This happens all the time, by the way. People doing these calculations in a rush, picking off the wrong variable. Just keep your variable straight. Okay, more questions? Right. So we will now work in the original units. All right, so I'm going to write out longhand what this means, standard units. So standard units means you take your value, you subtract off the average of y, you divide by the average of y. Then you take, that is equal to r times, here is x in standard units. Do you agree? I have taken the equation that we just used and written out the standard units longhand. Yep? Anything mysterious there? Okay? So if I sit down with a pencil and I do the algebra, I should be able to just isolate estimate of y on one side and have everything pop out here. Yes, I should be able to just manipulate this equation and get the equation in the original units. That's boring, but it can be done. Why don't we instead look at a picture here? The first picture we understand very clearly. The regression line passes through, this is in standard units, it passes through the origin. For every SD you go over, you go up only R SDs. Yes? So if you redraw this picture in the original units, then this point becomes the point of averages. Yep? So your regression line goes through the point of averages. And then if you go over an SD of x, you don't go up a full SD of y, you only go up R SDs of y. Distances are now measured in SDs. Yep? So a distance of 1 on the horizontal axis is 1 SD of x. A distance of r on the vertical direction is R SDs of y. You see that? Okay, take a look, absorb, and ask me any questions about the translation between those two figures. Okay, well, if that's clear, then from the second figure, can you tell me what the slope of the regression line is? Definition of slope? Rise over run. Yes? You should be looking at R SDY divided by SDX. Yep, that's the slope. And the intercept you can figure out if you do the algebra. This is why some long-suffering high school teacher taught you the point-slope form of the line. You know a point that the line goes through, that's average x, average y. You know its slope, and so you can find the intercept. We're not going to do that here. We're just going to tell you what it is. You can go take the pencil and work out the algebra if you want. Slope and intercept of the regression line. Slope of the regression line, R SDY over SDX. The intercept comes out to be, you take the average of y, that's not quite the intercept. You subtract off the slope times the average of x. And you can work that out easily by algebra, or you can just remember. And since we're going to want to draw zillions of regression lines, especially when we start bootstrapping scatter diagrams, we are going to want functions for all this stuff. And so what I've done is I have written functions that we are going to use every single time. I expect you to be able to write all these functions. Standard units, each one is a one-liner. Standard units, correlation, slope, and intercept. In that order, because you need the previous ones to do the next. Okay, so I've got a function called correlation, one called slope, one called intercept. I would like you to go back and take a look at them and just convince yourself that they're doing exactly what they're supposed to do. And I want to show you something. The correlation in Galton's original figure was about 0.32. There's the slope and the intercept of the line. So the equation of the line is your estimates of child height is 0.64 times given mid-parent height plus 22.64. That's the equation of the line. What I would like to do is show you how close or how far it is. These were our original predictions, those gold dots that we've been looking at for weeks. These are our new predictions. They're exactly on the line, based on the slope and the intercept that we just found, right? And that's what the picture looks like. Okay, I apologize for this gray color is the data science default. So you can see the very, very dark blue points are the same points that we had. Somewhere underneath are these gold points that were our original estimates. And the reason you can't see those gold points really well is that this gray straight line is going right over them, right here. Right? My old eyes can barely spot the gray straight line. And what this is proof of concept that the line gives you the right thing. Friday, we will talk about errors, right? How good is this estimate? And then move to other shapes of scatter diagrams.